Hello and welcome to another video. In this video we're going to be working on count the number of houses at a certain distance to, and it's going to be the last problem from weekly contest 381, and it's also the same as the second problem, just with a much tougher constraint. And I think this is the first problem I've done on my channel that's an 8-point difficulty problem on the contest. It's pretty rare, so yeah, let's get into it. So you're given three positive integers n, x, and y, and in a city there exist houses 1 to n connected by n streets. And there's a street for all of those. There's also an additional street from x to y, and you want to return one indexed array where the result is the total number of pairs of houses, such that the minimum streets required to reach one house from the other is k. Note that x and y can be equal. So let's kind of look at this. So from house 1 to house 2, what's like the shortest distance? It's 1. Then from house 1 to house 3 is also 1. From 2 to 1 it is 1. From 2 to 3 it is 1. From this is 1. So every house has a distance of 1. So all these combinations, 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, 3, 2, all have a distance of 1. So we want to return an array of 6, 0, 0, meaning of distance of 1 there's 6 houses, or just 6 combinations. Distance of 2 there's 0. Distance of 3 there's 0. Okay, let's look at the second one. So once again, if we go to house 1, the distance between 1 and 2 is 1. The distance between 1 and 3 is 2. The distance between 1 and 4 is also 2 if you take this route. And the distance between 1 and 5 is 3. So that's kind of how you calculate. You basically just figure out from every house to every other house, calculate the shortest distance. And sometimes you'll take this path, sometimes you won't. You might even like go backwards taking this path, depending on how this is. So essentially, they show you all the pairs again. So for 1, it's 1, 2, 2, 1, 2, 3, and so on. So one quick optimization we'll make is we will only calculate distances for every houses in increasing order. So for example, we'll count 1 to 2, 1 to 3, 1 to 4, 1 to 5, but we're not going to calculate the reverse, because if 1 to 2 is, let's say, distance of 1, that means 2 to 1 will also be a distance of 1. So our two houses, every time we calculate these two, will always be in increasing order, and then we can just double it to get the reverse, right? So we'll have like 1 to 2, 1 to 3, 1 to 4, 1 to 5, get those distances, and then double them all to get the reverse, to get 2 to 1, 3 to 1, 4 to 1, 5 to 1, and so on. And so here's another example. So notice that when x and y are equal, this extra path will never be used because the house will basically just lead to itself. So there's no point there. And so they show you these numbers again. So the first thing we have to try to solve is, let's say we have 9 houses, and let's get this distance array for 9 houses, assuming there is no extra path, because that's going to be what the crux of this problem is going to be, and then there's going to be a bunch of sub-problems without this extra path. So assuming just the houses are linked like this, right, 1 to 2 to 3 to 4 to 5 to 6 and so on, and there is no extra path. So how many connections can we make? So from 1, we can connect to 2, 3, 4, 5, 6, 7, 8, 9, right? We can connect to every single one of those. So 1 to 2 is going to be distance 1. So let's write that in. So 1 to 2 is going to be distance 1. 1 to 3 is going to be distance 2. 1 to 4 is going to be distance 3. 1 to 5, distance 4. 1 to 6, distance 5. 1 to 7, distance 6. 1 to 8, distance 7. 1 to 9, distance 8. So these are all the houses that we can build from 1. Now let's do the same thing with 2, and then you'll start to see a pattern. So from 2 to 3, there's distance 1. From 2 to 4, distance 2. 2 to 5, distance 3. Then distance 2 to 6, distance 4. 2 to 7, distance 5. 2 to 8, distance 6. 2 to 9, distance 7. So notice how the houses with 1, we could build 8 of them, 8 different ones. But then with 2, we can only build 7. So if you actually do the same thing with 3, you'll get the same pattern, but you can only build 6. Because we're only doing increasing order, right? So you can go 3 to 4, 3 to 5, 3 to 6, 3 to 7, 3 to 8, 3 to 9. There's only 6 of them, and the farthest one is distance 6. And this will basically keep happening. So the number of houses, let's just focus on each house by itself. The number of houses that we can build of distance 1, how many is that going to be? It's going to be 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9. So let's count those, right? So 1, 2, 3, 4, 5, 6, 7, 8. So there will be 8 total houses we can build of distance 1 here. So this is going to be 8. Then distance 2, there will be 7. So notice that all of these houses we're able to build a house of distance 1. If you just take that house and the one after it, that can be 1. But now this house 8 can't be used to build something, can't have a distance 2 to anything, because the only thing, remember, we're only going forward, this is the only one. So here there will be 7. And then for distance 3, this one now can't have it. So this will be 6, 5, 4, 3, 2, 1. Now you obviously want to double it at the end to actually calculate for the reverse. So really it'll be like 16, 14, 12, and so on. So there is a pattern here, right? So you can say that, well, if I'm trying to build, and if I have a bunch of houses, 1 to n, then distances will be n minus 1 down to 0, right? All the way down. And so that is indeed true. But there's kind of another way to do this without doing this. And you could probably solve it like this, but there's like another cool thing you can do that makes a lot of sense and that I'm going to be using. And that's basically we can figure out for each house what's its contribution. So for house 1, how many different distances can we build? Well, we can build 8, right? Because we can go all the way from 1 to 9. So we can build a house 1, house 2, or distance 2, distance 3, distance 4, distance 5, and so on. So for house 1, we can have distances 1 to 8. So what you can actually do is you can do this with a prefix sum. And the way to do this with prefix sum is you start at the first distance you can build. So for house 1, we can start here. And then we want to decrement right after the range that we can't build. So for house 1, we can build in 1 through 8. So the one right after is 9. So we're going to have a negative 1 here. Then we're going to do the same thing for house 2. So house 2, the first distance you can build is here. And for house 2, you can build, what's the distances you can build? So the farthest you can build is 7. So there's going to be a negative 1 here. Then for house 3, so for house 3, it's going to start here and here. For house 4, it's going to start here and here. For house 5, it's going to start here and here. House 6, house 7, house 8. And house 9 can't build anything because remember we're only doing to the house after it. So if we actually add all these together now, so this will be 8, right? Because 8 houses can build something to the ones after it. But so now that we have this, we can actually build a prefix sum. So let's take a look what that will look like. So this will be 8. This will be the old value minus the current value. So this will be 8 minus 1, which will be 7. This will be the old value minus the current value. So 6, 5, 4, 3, 2, 1, 0. So notice this is the same thing, right? So what you can do, we can write this. So as a general use case, we can write that for a house, we just have to figure out how many distances it can make. So for example, 1 can make 8. So if it can make 8, so for a house, increment distance array at first place it can make a house, right? So in this case, it would be at distance 1, or the distance like here. At first place it can make a house, and decrement right after it can't, right? So increment, so for example, for house 1, the first place it can make a house is at 1, right? It can make a house of, or distance 1, and the last distance it can make is 8. So that means we're going to increment at 1 and decrement at 9. We do that all, and then we do a prefix sum at the end. Then do prefix sum at the end to get distances. And so that's kind of like the crux of this problem. So you can do this for anything that doesn't have this like optional path, right? As long as we have a linear path of houses, we can do that. We can figure out, okay, like in this example, this 1 can make 3 distances. So 1, 2, 3. So we can say we'll increment at 1, and then we will decrement at 4 because it can make 1 through 3. So basically you have a range, right? 1 through 3. Increment at 1, decrement at 4. And that's how we can do that. So now we basically have to break down this problem into like what are the optional routes to take. Not optional routes, I guess. What are like the optimal routes to take. So to do that, let's actually draw this. So this should be good enough. So essentially, let's say these are all our houses. So we have 9 houses, and we can number them, right? So this is house 1, 2, 3, 4, 5, 6, 7, or maybe 10. Okay. And let's say there's a path over here. So this is the X and the Y. So basically this problem needs to be broken down to 3 parts. 1, houses before X, houses between X and Y, and houses at Y plus. So the houses at Y plus is going to be, we pretty much did that already, right? So every house here Remember, we're only going forward and then we're multiplying it by 2. So we need to go 8 to 9, 8 to 10, 9 to 10. So all of these are never going to use this like optional path, right? So because they never use this optional path for these, you know the distances from this problem before. So this is a really easy one, right? Like 8 will go distance 1, this will go distance 2, this will go distance 1. This is literally the same problem before, where you're just given an array of 3 houses, right? So you can just imagine you have an array of 3 houses with no optional path, and then how many distances are there. So that part is done, right? So this is done. So let's do the rest of it. So the issue here comes up with the houses before X. Depending on where they're going, sometimes they'll use the optional path and sometimes they won't. So for example, if we go from 1 to 4, we definitely don't want to use optional path, right? Because it'll take 1, 2, 3 steps here. And if we use the optional path, then it will go 1, 2, 3 over here, 4, 5, 6, 7. So that's really bad, right? So there's going to be like some houses that you are going to want to use an optional path and some you're not. And the way you can kind of figure out like what point, like what you're going to also realize is after some point, you will always use the optional path. And before some point, you will never use the optional path. And this point will be the same if you're looking for houses before X. This point will be the same for all of these. So for example, let's say you start it here. There will be some house that you're going to that you will never use the optional path. And after that, you will always use it. So in this case, basically you can try this with like trial and error and just trying some math. You will always use, you will never use the optional path at every house before the left half of this. So if you just take the left half, this can be even or odd. If it's odd, we can plug in an odd and see what happens as well. So if it's even, every house at this point or less, right? So 1 to here, 2 to here, 3 to and so on, will never use the optional path. And let's kind of look at like why this will, like how this is true. So let's say we go from 1 to here. So this is 1, 2, 3, 4. Now let's say we take the reverse. So we would go 1, 2. We would go over here, 3, 4, 5, 6. So notice how it's slower, and all of these will be the same thing, right? Because starting here to get to here is 2, where going backwards would be 1, 2, 3, 4. Now let's actually move to this house and see what happens, right? So instead of moving from to 5, let's move to 6. So here it will be 1, 2, 3, and here it will be 1, 2, 3. So what's going to happen here is it's the same. So for this point, it'll actually be the same distance, taking the optional path or not, but we're just going to say for every point after the half, we're going to take the optional path because it'll be the same, right? So here this is 1, 2, 3, and here this is 1, 2, 3. And then every point after will obviously be better to take the optional path. So here it's tied, but everything here or less, it's always going to be better to not take the optional path. Now let's quickly add a, let's make this odd just to show this really quick. So let's just get rid of this thing and let's just add a box and then we'll change it back. So if it's odd, then it's the same thing. You're not going to want to take the optional path for the middle to the left. So this is 1, 2, 3, 4, 5, 6, 7, right? In this chunk. So any element here or less, you're not going to want to take the optional path. And so let's see why that is. So this distance is 3, and this distance is 1, 2, 3, 4, right? So that's why, as a simplification, like I said, just always take the middle and left, and don't take the optional path, and everything to the right will take the optional path. So for this is better this way, right? Now, if you go to the next one, let's say we want to go to over here. Now this is 1, 2, 3, 4, and this is 1, 2, 3. So for odd, anything to the middle. So let's say like our value is, like let's actually go back to this. Let's say this is 6, 7, 8, 9. Then we can basically do like a 9 minus 3, which is 6, and divide by 2, right? And then the value we'll have here is, I think I did that wrong, actually. It's 9 plus 3. 9 plus 3, divide by 2. So we'll have 6. So that's the value, so that'll work out, right? This is the value, this is the farthest value you want to go. And let's go back to our even example. So let's go back over here. So now this will be 8 plus 3, divide by 2, we will get 11.5 divided by 2. And like I said, we're just going to default to this value. So we will say it's going to be, did I do that right? Yeah, I think so. Yeah, so 11.5 divided by 2. Yeah, it is right. Which we will just floor divide, and that'll give us 5. So this will work out basically. So to figure out the farthest value you want to go to, let's write this down as like a formula. So to figure out farthest square to go to without using optional path, we do x plus y, floor divided by 2. So in this case, it's going to be this. So now that we know that, like for whatever cell we're on, let's say we're on this cell, we know that for every cell we want to go to, like we want to go to all of these cells without using the optional path, but then we want to go to every cell after it with using the optional path. So let's just figure out the without the optional path first. So that part's pretty easy, right? Now we're saying basically from here, like let's say we're on the cell, we want to go to all these cells without using the optional path. Well, that's just going to be the range that we had before, right? We're not using the optional path at all, so we can have a house of, or distance of 1, 2, 3, 4, 5. And then 6 is going to be invalid. So that we can just handle kind of like what we did here. So this left part, we can handle kind of like what we did the normal way. So that part's pretty easy. Now the right part. So the right part, you basically have to split into 2 sections. You have to split into, and we can actually draw this with the squares. So you're going to, like, all of these is fine, but the right part is going to be these 2 squares and then these 2 squares. So we can actually even handle it like in 2 ranges like this. We can handle it with this range and whatever is to the left of y that's after this like section here, right? There can be multiple things here. So let's handle this part first. So let's handle y, like we are to the left of x and we're trying to get to all of these. So that you basically have to figure out what's the distance from your current square to y, and just a bit, and you're always going to use the optional path here. So the distance is just going to be like, let's say we're over here. Distance is going to be 1, 2, 3. We figured that out. And then our range that we can build is just going to be, let's say y takes 3 length, and it's going to be 4, 5, and so on, right? So just get distance from I to y, then range will be that distance plus 1 for every cell after it. And so for example here, let's say the distances we want is going to be, let's see, 1, 2, 3, 3, 4, and 5. So if we want 3, 4, and 5, it's going to be the same thing with the prefix sum. The first distance, the first house you can make is going to be at 3, and then you can make 4 and 5, and then at 6 you'll put a -1. So it's all the same kind of thing. Now let's handle going from one of these to this part over here, right? Like if there's something to the left. So that's also kind of similar. You basically just have to figure out how many numbers are there to the left of y, right? Like you have to figure out what's the index of this, what's the index of this, how many numbers are there to the left. And then the first square you're going to be able to get to is going to be this square over here. So you calculate that. So this will be 1, 2, 3, 4. And then if you have more, you just figure out like how many squares do I have? And the distance will be the distance to here plus 1 for every single square after that. So that's going to be the same thing as this, just with a prefix sum. So in this case here, there's only 1 square, so let's do that. So distance is 1, 2, 3, 4, right? So at 4, we put in a 1, and then there's only 1 square, so at 5, we'd put in a -1. So that's how we'd handle this left section. So once again, to repeat, for everything to the left of x, you have to first calculate the distance to everything to the middle point of x and y, which is just a basic, completely linear thing that we did before. Then you have to handle y and after, which is just calculate the distance from wherever you're at to y. Always use the optional path. And then whatever that is, for every square after it will be +1, +1, +1, and so on. Then you have to calculate the distance to the thing to the left of y, if there is something between to the thing to the left of y and your halfway point, right? This is the halfway point. Calculate that. And then figure out how many more squares there are here, and then for each square add 1 to the distance. So this will go like 1 to 7, and then if there's more stuff here, there can definitely be more stuff here. Like let's say this was length like 50. There would be a lot of elements here, not just 1. So you have to figure out how many elements are there, and then your range would be like some starting location S, and then you would add 1 for every other square. And so you just do the same thing. You just add to the prefix sums accordingly at the start of the range, and you subtract at 1 after the range. That's why knowing how to do this prefix sum originally for this problem is the key to doing all of it. Okay, so now we handled everything after y, right? Because we know we don't need to use this. It's pretty straightforward. And we handled everything before x. Now what we have left is everything between x and y, and this is kind of like complicated. So everything between x and y is going to follow kind of a similar logic to what we had before, right? Basically, everything between, like let's say we start here. So if we start here, there will be some cells that we are going to want to take the optional path for. But now you're going to kind of have to go backwards. So instead of actually starting here, let's use another example. Let's say we start here. So this path, you can go forward or backward, right? But let's say we start here and we want to go to 5. Well, obviously to 5, we would just go forward 1 cell because that's going to be the fastest way. But what if we want to get to like 7? So if we go forward, we would take 1, 2, 3 steps. But notice we can also go backward. So we can go back here and then take the path and then go here. So that would also be 3. So if we wanted to get to 9, for example, we could go forward, so it'd be 1, 2, 3, 4, 5, or we could go backward and then take this optional path. So that would be 1, 2, 3. So it's going to be kind of the same thing where there will be a range where you're not going to want to take the optional path because it'll be faster, and then every number past that range will either be equal to take the optional path or faster to take the optional path. And that's kind of what you need to do. You need to figure out where the range is. So we're going to start at every element. We're going to start here, and then we are going to go to, we're going to try to figure out every element, like the starting location needs to start here, and then it needs to go to every element in here as well. So we'll start here, 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 here. We already did this part, right? This is going to be the easy part where it's just completely linear. But for here, we have to figure out like where we want to go. So in the beginning, like I said, you can do a little bit of math here and just try stuff out and then figure this out. So I would recommend for a lot of these problems, when you're not exactly sure like what's the point, like what's the halfway point, just try to have a few arrays of various length and figure out like what's the pattern and see if that pattern applies to like, if this pattern applies to an odd length array or an even length array, if your pattern holds, then it's going to be good. And it's hard to get like an actual formula. So generally what you just want to try is kind of like a guess and check. So here it turns out it's still the middle point. So it's going to start at the middle point. So in this case, it's an even length array. So the middle point will be the left middle. But if it was an odd length array, then we would actually have the middle. So if we had another square here, it would be here. So let's kind of show that as well. So if we're here, and we actually, I already did this earlier, right? I said if I start here, everything here will be optimal to just not take the optional path. And everything here and past will either be the same or better to take the optional path. So we already calculated this one. So for this square, we already know that like every square up to here is going to be better not to take the optional path. And this problem is just a basic completely linear problem, right? So for all of these starting, not for all of these starting location, for this starting location in particular, we know how to do this, right? Like we can build a house of length, or we can build distance 1, we can build distance 2. So we'd say at like, okay, at distance 1, let's put it in 1, and at 3, let's put it in -1. So we know how to do that. But let's see what happens when our x moves up, right? So like we know how to do this, but what if we start here now? So it turns out, like I said, from a decent amount of guess and check, your middle point will move up by 1 every time this moves up. So let's kind of show this, right? So this is length 2. Oh, and I forgot one more thing, I guess. So let's go back actually. So we know how to do this, but how do we do the rest of it? So the rest of it is going to be very similar to the problem before this one, where you basically just move to y, and then you split it into 2 parts. So you move over here, you do this section first, right, with this optional path. You calculate how long this is, and then you move to y and you do this section afterwards. Going to be literally the same as this. Just figure out like how many things there are, what are the distances, what range do I need to add. Okay, now we can go forward. So let's say we are now here. Like I said, by doing guess and check, the optimal distance is going to move up by 1 every time this moves up. So, but obviously like, Yeah, and then once it gets to y, then you can basically what I did in my code is once this gets to y, then I'll just get rid of the optimal distance, and I'll know like I would just never want to take the optional path anymore. And that makes sense, right? Like let's say we start here, obviously like everything past this, we're never going to want to take the optional path. So for this, let's say we're trying to get to this cell. This would take length 2. Now let's say we try to take the optional path. So this would be 1, 2, 3, 4. So it's better. Now let's move this up 1. So let's say this is over here. Let's say we're trying to get to here. So this is 1, 2, 3. And now this, you can kind of tell, right? Every time you move it away, this distance will go up 1 and this distance will go down 1. So now this is going to be 3 and this is also going to be 3. So they're equal. Now, like I said, if this was odd, they might not necessarily be equal, but this optional path will always be better or equal to this midpoint. So you notice how the midpoint started here for this x value, but then as this x value went up, this midpoint went up. So yeah, so now you do kind of the same thing. You just keep moving your midpoint up with your x value until it's equal to the y, and then when you say when it's equal to the y, you just say like, okay, from here on in, just don't take my optional path at all. Every other square will just be completely linear from here. So yeah, so here you basically do this, doing the normal thing we did before, right? So for all of these, this is distance 1 and 2, make the prefix, get rid of it. And then for the rest of it, so for this part, figure out this distance. It's going to be the same as the old one, except it's going to be one more cell, right? Because as you move up a cell to go backwards, you'd have to move back one more cell. So figure out this distance to y, and then from there, figure out how many cells are there here and how many cells are there here, and then do the prefix sums. So let's just keep going. So for this cell, if we start here, now the middle distance will be here, and we can show that again. This is 2, and if we go backward, it will be 1, 2, 3, 4. So same thing, right? So finally, for here, this distance will be y. So you know for here on in, you're never going to want to take the optional path. So now we can basically just get rid of this middle point, and we know like from here on in, from this number to everything up until y, we already did this chunk, right? But for everything up until y, we can just do the forward part, right? So for 6, we'll figure out how many things can build 1, 2, 3, 4. That means put a 1 at the 1, -1 at the 5 as always. Then here, how many things can it build? 1, 2, 3. So put a 1 at the 1, -1 at the 4, and so on. And that's going to do the middle part for you. And so now we did the left, right? We did the left by figuring out where the middle was, and that one never moves. So from the left, there's always some optimal midpoint where you don't want to take the path. And then everything after that, you do want to take the path. We did this part here, which is just completely linear. So that's the easiest part. And then we did everything from x to y. And from there, the midpoint starts at the left middle, or the middle if it's odd. And then every time your number moves to the next cell, this midpoint moves. So it'll go to here, to here, to here, and so on. And once you add all those up, you basically have this prefix sums array. And then you can get them all with just doing a prefix sum. And then remember, since we only calculated, like for example, our houses are going to be like 1 to 2, 2 to 3, 3 to 4, and so on, we have to get the reverses. So whenever you get this prefix sums array, just double everything, and that'll give you reverses, right? So if 1 to 2 had a length of 1, that means 2 to 1 will also have a length of 1, and so on. So we're just calculating only going forward, and then to get the reverses, you just take all of these numbers and multiply by 2. Because if there's a distance of 1 from 1 to 2, there's a distance of 1 from 2 to 1, and so on. Okay, so that was kind of a lot. So let's take a look at the code. And I will say I could have definitely made this better, but I was doing this kind of late, and I just refused to refactor. So I think these kinds of problems are, like I said, even once you saw the solution, it's still very hard to code in my opinion. And there's a lot of like edge cases and so on. So definitely could have made this cleaner. But yeah. So essentially, like I said, you make a distance, and in my picture, I had them all 1 indexed, but in the actual code, I have them 0 indexed. Now, I think what you can do to make it easier on yourself is you can probably make a array of length n+1, and then you can just put in these numbers, and then finally at the end, get rid of this, right? Just slice off this last part. And I think that'll make it easier to because it's kind of annoying to switch from 1 indexing to 0 indexing all the time. So what you could do is you can just make a 1 index array, put nothing here, fill out these, and then just get the slice at the end here. I think that would make it a lot easier. So I basically had a check in the beginning if x was y. So if x is y, then this like optional thing is not used. So then I just do the basic prefix for every single number. right? So for every single number, put a 1 at the 1 and put a -1 at wherever it ends. So that's basically what I did here. Just figure out like, or first I multiplied it, but that doesn't really matter. So first I multiplied it by 2 to get the left and the right. And then, yeah, you just basically say, okay, let's get the distance and let's just return back. And that part should be pretty easy. So then I make sure that the x is less than y, so I don't have to worry about a bunch of edge cases. So if x is here and y is here, then this is fine. But if x is here and y is here, it's the same problem, so I just reversed it, right? Like, it doesn't matter where x and y is, so I just said, like, if x is to the right, just reverse them, so x is always to the left of y, just so I don't have to, like, worry about which way am I going. So that part's pretty straightforward. Then, basically, you get the prefixes from y to the end. So, like I said, figure out, like, at house 0, put in a 1, and then wherever that range ends, put in a -1. And these indexes are kind of hard to get right, but yeah, it's essentially for once we have our houses for this part of the range. This is, like, the easiest part of the problem. Then we figure out the midpoint, right? So we figured out the midpoint wherever that is. So like I said, the middle of x and y. And then we get this chunk, which is completely linear. And then we get this chunk, which is also linear, but it starts at whatever distance this is, right? From x to y. And then we have to get this like left chunk as well. So we have to get these two chunks and this chunk over here. And yeah, like I showed, so actually it won't be like this chunk, sorry. It'll be, so we get this chunk, then we get the chunk of this. So this we have to calculate the distance from this number to y, and then the chunk we're actually getting is going to be this chunk and this chunk. So that's kind of what we did here. So you figure out the distance, the y location, like how long it takes to y, and then you figure out y to n and m to y minus 1. So basically I called m this value here, and y minus 1 would be over here. So figure out like how many cells there are in between here. And do the prefix stems appropriately. And then finally you have to do x to y. So you have to get the midpoint again, and you have to do kind of the same thing. And then I just said, so the y location is a little bit tricky when you're going from x to y, because you don't really know if it's faster to go forward or backward. So I just said, wherever I'm at, let's figure out if it's faster to go forward or backward, and let's get the minimum of those. Where if you're before y, you're always going to want to take the path. So that part took me a little while to figure out. Then figure out the distance from y to n, like how many things there are, right? So, or not the distance from y to n, but basically just fill out all these squares from y to n. And then finally, you have to do the other part as well, where you have to get the section here. So even though you are in here, you have to get the section from y to here. So this part, then this part, and then also wherever you are to the midpoint. And remember, your midpoint keeps moving with your number, so that's what I did here. So I just incremented my midpoint. And I incremented it up until it was y minus 1, because I don't want it to get past y, because I had some other random cases there. So essentially I just made my midpoint go up to here, which is fine. Like that's just personal preference. You can also just say once your midpoint like that you're getting to gets to y, then whatever cell you're at in between x and y, like let's say your midpoint is here, then it's just a linear search here, and you don't need to do any left or right or anything. So that could make the code easier. Then finally you do so the distances just had these pluses and minuses, so it just had a bunch of pluses and minuses. Then I just went through all of them, multiplied them all by 2, and did a prefix sum. And if we run that, it's pretty good. So this did take me like I want to say like an hour or two to debug, because like I said, I was really stubborn on like not rewriting the code. I kind of got what I need to do. I thought it was going to be a lot easier than it was to debug. I was like, oh, I'm so close, and then I kept getting like one more edge case. And so yeah, definitely could have wrote this a lot cleaner. And this doesn't need any special like data structures or anything, but it definitely is quite difficult to figure out how you can do this in O of n, because basically for each house you need to be able to figure out how many houses it can make in O of 1 time, which is not easy. So hopefully this is helpful for you. Let me know what you think. Oh yeah, so we can write the time and space. So times O of n, space is O of n. I did see a heap solution where someone basically, I think, wrote like the length of available distances and always took the shortest one. Makes a little bit of sense, ran a lot slower, but might be a lot easier to code. But yeah, So let me know what you think about this one. I do find it's often hard explaining these like super hard problems because it's like there's so much. So I don't know, like if you want me to explain anything in more detail or worse, just let me know like how I do, how or what you guys think about these like super hard problems. If I need to improve on anything, because there's not too many, right? There's at most one a week or something. So let me know about that. And if you did like this video, then please like it and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.